We've been talking about ideal gases, and now we're going to talk about real gases. In an ideal gas, there are no attractions between the gas particles, and the particles have a negligible volume. Real gases act like this under many circumstances, especially at STP. So here, if we look at the actual molar volume of some real gases compared to an ideal gas, we see that the ideal gas would be 22.41 liters, and the others here are remarkably close, right? Helium is actually the same, 22.41. We've got 22.40. These are all very close. So real gases act a lot like ideal gases at STP, which is why we can use the ideal gas law at all. But there are some conditions, namely high pressure or low temperature, where the differences start to become important. So the effect of finite volume of gas particles. So here we have argon gas at a low pressure. There's lots of space between the particles, right? And so the size of the particles don't matter. This is Wyoming, okay? Now, if we increase the pressure that is pushing the particles closer together, now we're approaching the elevator situation. As they get closer together, the size of them matters more. If it was an ideal gas, you could get smaller and smaller, and it wouldn't matter because they have no volume, but real particles do have volume. So at higher pressures, the argon atoms are occupying a significant part of the volume, and so the actual volume is greater than we would expect because of the actual volume of the particles. So here we have argon in green and the ideal gas in red. So down here at low pressures, 200 atmospheres, that's pretty high, right? Down here, their volumes are the same or extremely close. We don't see a difference until the pressures get really, really high, and now we see that the argon is occupying a larger volume than predicted by the ideal gas law. And that's because argon particles are real and they do have volume. So there's a guy named van der Waals back in 1873 who's trying to correct the ideal gas law to make it work for real gases. And I'll just, spoiler alert, we're not going to do anything with this messy equation. So he found that he could add a correction factor. So here's the ideal gas law, V would equal nRT over P, but the real gases took up more space, so he added a correction factor. And so B was a constant, was different for each gas because their molecules are different sizes, and N was the number of moles of gas. So it can be done. Do we care? Absolutely not. What about high temperatures? High temperatures, the gases, the pressures are nearly equal for ideal and real gases. Because at high temperatures, gas particles have high kinetic energy. They're moving very quickly, and when they hit each other, there isn't time for them to have any interactions. But at low temperature, the pressure of gases is less than the ideal gas law predicts, because those collisions at lower kinetic energy, at lower speed, now there's time for the particles to actually interact with each other. So you think about, people falling in love, right? So say you're on the streets of New York and everybody's walking really fast, and you're walking fast in the opposite direction. Are you likely to fall in love with someone you pass on the street or even bump into? No, there's no time, right? But what if you're sitting in a classroom with this person for a whole semester? Something could happen. It's more likely, right? So gas particles at high temperatures are moving so fast they don't have time to get into relationships, right? But when they slow down at lower temperatures, now they're like, ooh, you're kind of attractive. And so when they bounce off of each other, it's a little slower than ideal gas behavior predicts. And so we see that the pressure is less than we expect. And so van der Waals corrected for this as well. And so here we're subtracting a term. This graph shows how at low temperatures, ideal gas behavior and real gas behavior is different, but at higher temperatures, they're the same. And there's the whole van der Waals equation. Isn't that a mess? And I'm not sure why. They give you these different values for those van der Waals constants. We're not going to do anything with those. Ugh.
Do we do that in Chem 1B?
No, we're not going to use that in Chem 1B either. I think the point of this, because, well, why do they even mention it? The point of this is that you can have equations that accurately describe the behavior of real gases. They're just a lot more complicated. In some situations, you would need those. If you're an engineer and you're dealing with something at a really high pressure or at a really low temperature, then yeah, those things are going to matter. But most of the time, doesn't matter. So this is showing us some of the differences between real and ideal gases. So we're looking at PV over RT as a function of pressure, so that's N. And we would expect for an ideal gas that we'd have a constant of 1. Here we see that some gases are always above that, and some gases are always below that. The ones that are below is because the interactions between these particles are more important. So water molecules actually have a lot of attraction for each other, and so we're going to see them always being below the line. Helium particles have very little attraction for each other, and so that's not really ever going to be an issue for them. So up there it's molecular volume that's the most important, and down here it's attraction.